Hello juniors, today we're going to see electronic assignment number 14, which is list square regressions. This is probably the most important tool that you're going to learn with respect to bivariate analysis. And okay, so just pay attention to this lesson and you shouldn't have much struggle with this. It is a pretty easy topic once you learn how to do it in the calculator, and it has a lot of applications in real life. Okay, so list square regressions. There are four main objectives for this class. The first one, determine the linear correlation of bivariate data, which is something we have been doing already in the previous classes. Number two, find Peirce's product moment correlation coefficient R, which is also something that we already know how to do to determine the value of R. Find the equation of the regression line y on x. This is something new that we're going to see. Last class, we've seen the line of best fit, which is kind of like this regression line, but it's very inaccurate. What we're going to see today is how to calculate the exact value of the regression line, so this is very accurate. Finally, we're going to use this equation for prediction purposes. Okay, so from the previous classes, we have seen that we can draw the line of best fit or regression line by eye. This method may be very inaccurate though, as I told you already. So we're going to see where this method comes from, this accurate method comes from. It says there's another way to improve our line involving residuals. What are residuals? Here it says a residual is the vertical distance between a data point and the graph of a regression equation. So if you see this graph over here, you will understand the concept. You see that we have points plotted in this scatter diagram, and then there's a regression line traced which kind of shows the trend of these points. In this case, this is a negative linear correlation, right? So if you see the line and we compare it with the plotted points over here, we would see that for each point there is this. If we focus on this point, this is the actual data point that we obtain from a specific data set. Then we have this distance over here, the green one, which represents the residual, and it basically is the subtraction of the predicted value minus the actual data point. Okay, so that's the distance over here, and that's what we call the residual. So for each point we have the residual. In this case, it's this point over this distance over here, and this point is a very short distance, then this one, and so on. Okay, that is what we know as residual. Okay, so that's the concept of residual. Once again, if we read the definition, it says it's a vertical distance between a data point and the graph of a regression equation. Okay, so what is the regression line method about? It says the residual is positive if the data point is above the graph, as you see over here. The residual is negative if the data point is below the graph, which is this point over here. Then the residual is zero only when the graph passes through the data point, which is this point, for example. Then it says, a method called least square regression will help you find the most accurate line of best fit, and therefore help you to make better predictions. So here it says, the least square regression line is one that has the smallest possible value for the sum of the squares of the residuals. If you take a look at this graph over here, we have traced all the different residuals, right? The distance between the data point and the predicted point with the line, okay? If we square these distances, if we take this side squared, basically what we're doing is we're building a square. You see that the area of a square is a side squared, length squared, right? So if we square the value of the length, we're building the area of a square, okay? Length squared. Why do we square each of these values? we square each of these values to eliminate the negative numbers, okay? You see that this point over here produces a negative residual as well as this point over here, but when we square that negative value, it turns out to be positive. So all of these squares, the areas of these squares, are positive, right? So the objective of the least square method is to minimize the addition of these areas, okay? Minimize sum of areas. That's what this method is about, and that's the one that creates the less inaccuracy, right? Or the one that is the most accurate, we would say. Okay, so we're gonna do a short investigation just to prove this, and you can try this on your own if you want. You may copy this link over here into your Explorer, into your browser, and you can do the simulation. I'm going to show it to you here. So here we have a set of points, right? A scatter diagram. And we would like to trace a line that shows the trend of this line, of this point. If you see this point, you can kind of think that there's a positive linear correlation, right? So let's try building a line. This is a line which I can modify its slope, and I can modify its value of b, which is the y-intercept, right? So we can have these two effects on the line. So let's try to put this line in a way that it kind of models this point. So maybe I'm gonna guess it's something like this maybe. We have 2 points up, should be a little bit up, maybe something like that, okay? So if I show the squares that are formed by looking at the residuals, you'll see that whenever I make movements of this, the values of the square either increase or decrease, right? That's if I modify the slope, and if I modify the y-intercept, we have the same effect. So the idea is that we should obtain we should minimize the sum of the areas of all of the squares. So I'm going to show the sum of the squares right here. So in this case, the sum of the squares is giving 13.3. If I modify this point, you'll see that it decreases there to 12.3. Then if I go the other side, it increases to 14, 15, and so on. So I want to minimize this value, so I will go to, let's see, what's the minimum point? 12.1. Let's see if I can stay there. Yes. 12.1 seems to be the smallest value. Maybe if I modify the slope, I'll get different values. 12.1, can I get something smaller? No, I think not. So we're going to go back to 12.1. There you go. Now, this program calculates the exact value of the line of the regression line. And if I show you this, we'll get this line over here. So you see that we've missed the line of best fit. Actually, it should be much more inclined down, right? So let's try, remember this value, 12.1 is the sum of our squares. If I try to replicate this orange line over here, let's see what the value of the squares would be. Let's see, if I need to change first of all the y-intercept. Let's make it there. And if I change the slope to make it match the line, cannot make it match perfectly, but we can make an estimation there. You see that we get a value of y. You can barely see that, but it says 10.55, so that's definitely less than 12. Okay, so technically this is the line, the regression line, the most accurate regression line, because it minimizes the squares. Okay, so that's what this method is about. Okay, so going back to the electronic assignment, there's a formula to calculate the regression line. And it says the formula for finding, the gradient or slope of the regression line is this one over here. The slope, or m, equals the covariance of xy divided by the covariance of x squared. Remember, we've seen these terms when we talked about when we calculated the correlation coefficient R. Remember? There was a formula, which I think it was covariance of xy divided by covariance of x times covariance of y, something like this. Okay, so same thing applies here for to calculate the regression line. So the covariance of xy is calculated this way, and the covariance of x is calculated this way. And here it says the sigma notation is a Greek letter S and is used as an instruction to sum all data. Sigma xy means the sum of all the xy values. Okay, so that's how you interpret symbols. Here's a very important observation. You are not expected to know this formula for an IB exam. You shouldn't know this, and this is not in the formula booklet. We're always, during an exam, we're always going to be calculating the regression line equation directly using calculator. Okay? The only moment where you are supposed to do these calculations is when you work with this in your math project, which you should do next year, okay? So don't worry much about knowing these formulas. I'm just going to show you one example, which we're going to be doing one only, just for you to understand how this formula works for the future, okay? Then, exam hint. You will be expected to use technology to find the equation of the line of regression during exams, which is what I just told you. Okay, so let's see one example where we're going to apply these formulas for the first and only moment in your life, and you're going to see that it's pretty easy. So this is a very simple example. It says, use the least square regression formula to find the equation of regression line through these points, 1, 3, 2, 1, and 3, 5. From the diagram, okay, this is from another textbook, so I'm just gonna erase the page from the diagram. I'm gonna leave it as, there you go. Okay, so to make this a little bit shorter, I already prepared the table that we have to consider to apply these formulas over here. So we're just going to apply the formulas directly. But basically what I did is, these points, all of these points have x and y coordinates, xy, xy, xy. So I made a table where I wrote the x in one column, the y in the other column. I represent the number of data I have. In this case, we have 3 pieces of information. And then I calculated these terms, xy, which is x times y. It's basically 1 times 3, which is 3. 2 times 1, which is 2. 3 times 15, which is 3 times 5, which is 15. Okay? And then I calculated the x squared column, which is just squaring these values over here. 1 squared is 1, 2 squared is 4, 3 squared is 9. And then I added all of these terms, all of these columns, this one, this one, this one, and this one, because the formula tells me to add those, okay? Sigma notation represents addition. That's why I did this table over here. So, what do we need to calculate? We know that the slope is covariance of xy divided by covariance of x squared. So, first of all, we're going to calculate covariance of xy. Covariance of xy equals, if we use this formula we have over here, it's the sum of xy. The sum of xy is 20, this one over here. Maybe if I write sigma over here, you would understand that these are all the added values. So it's 20 minus, according to our formula, minus what? The sum of x times the sum of y. The sum of x is 6. 6 times the sum of y, which is 9, divided by n, where n is the amount of information we have in our data set. In this case, it's 3. Okay? So, we calculate the covariance of xy, and this gives us, I think we can do this without a calculator. This is 20 minus 3 times 9 is 27. No. 2 times 9, 18. This gives us 2. This is 20 minus 18, and this is 2. Okay? So the value of the covariance of xy is 2. Then we want to calculate the covariance of x squared. Okay, so I'm going to apply this formula. The covariance of x squared is the sum of x squared. So this x squared, this column over here, we add all of those values and we get 14. So 14 minus the sum of x and the result squared. That is different from this because here we need to observe this value over here and then square that value. So this would be minus 6 squared. I'm going to take this a little bit down just to avoid confusion. Divided by n, where n, we know it's 3. Okay, so we solve this and we get 14 minus, this is 36 divided by 3. That's 13, no, 36 divided by 3, 12, right? Yes, 12. So minus 12. So this gives us 2 again. This is just a coincidence, okay? It's not something that always occurs. So finally, we can calculate the slope. We know that the slope is this. So the slope is covariance of xy, which is 2, divided by covariance of x squared, which is also 2 in this case. So the slope of this line is 1. So remember, the regression line equation is always, I'm going to write it here, y equals mx plus b, right? We actually, when we talk about, well, we're going to see that in a while, but when we talk about regression line, we call the m a also, but it's the same thing. It represents the slope. Okay, so we just found the value of m, this one, and now we need to calculate the value of b in order to have the equation of the line. How do we calculate the equation of b? If you remember from the previous class, we said that the regression line always passes through a specific point, which is the point mean of x, mean of y. That's always true, okay? So we need to calculate that point. Let me write that here. So y equals mx plus b. We already have the value of m, and we know that the point x mean, y mean is a point of the line. So we want to calculate mean of x. How do we calculate the mean of x? It's the addition of all of x, which we already have, 6, divided by the amount of data, which is 3. So this would be 6 divided by 3, which is 2. Once again, we're getting a 2 here. Then the mean of y is the sum of y, which is 9, divided by the amount of data, which is 3. So this is 9 divided by 3, which gives us 3. So the mean point has coordinates 2, 3. So that's a known point of our line. So finally, we can calculate the exact equation of our line, which would be, if I replace this point, it'll be 3 equals m, the slope is 1, times x, which is 2, plus b. So then by solving for b, we get that b equals, this is 1. 3 minus 2 equals 1. So finally, the equation of the line is y equals 1x plus 1, which is the same as saying x plus 1. So this is the exact equation of the regression line. With this equation, we can make predictions about this data over here. Okay, so that's how we calculate the exact equation of a regression line by hand, which we're not going to do all the time. I just did this for a simple example for you to understand how this formula works. Okay, finally, I'm going to show you how to do this using your calculator. It says parameters in the regression line equation. The regression line, as I told you, has this form, y equals ax plus b. What does a represent? And here it says a is the gradient of the regression line. It represents the rate of change in the y variable as the x variable changes. And what does b represent? B is the constant or independent term of the line. It is the value at which the line crosses the y-axis. We know that as the y-intercept. And it represents the value of the y variable when the x variable is 0. Okay, so it's basically the y-intercept. So let's see this final example for you to understand how to do this using the calculator. It says, as a car's tire becomes worn, it uses more fuel to travel the same distance. This table shows the age of tires and the number of kilometers the car traveled on 1 liter of diesel. So you see how useful this tool can be. And this is something that normally occurs in real life, and it's something that interests people to know, right? Who wouldn't like to know how much my car is consuming for every year of my of usage of my tire, right? So this is something pretty useful, and anyone could make an experiment about this and would get interesting results. Okay, so we have the table where we have the age of the tires from 1 to 6. So this person used a tire for 6 years, and this person recorded the consumption of diesel of his car, his or her car, right? Basically, this person wrote down the number of kilometers he or she was able to travel per liter consumed, per liter of diesel consumed, okay? So the first year, this person traveled 20 kilometers per liter, then 18.5 kilometers per liter, then 17.4 kilometers per liter, and so on, okay? Remember, this notation over here is the same as saying, if I zoom in here, this is the same as saying, this is the same as kilometers per liter, okay? So you see that as time passes, what happens to the distance covered per liter? It goes decreasing, right? Which is logical. As the more worn is the tire, the less it will travel per liter consumed, okay? So that's completely logical. So part A says, write down the regression equation. So finally, I'm going to show you how to calculate this using your calculator. So we're going to go to the calculator for a second. Just give me a second. I'm going to... Okay, so now you're able to see the calculator here, right? So how do we plug in this information? You need to go to Menu, Statistics, number 2, and you have, you already know this, list 1 and list 2. In order to save some time, I already plugged in the values, but what you do is, for list 1, you plug in the age in years of the tires, which is the independent variable from 1 to 6, which is what we have as data. And in list 2, you're going to plug in the dependent variable, which is kilometers per liter. And we have these values over here. Then, to calculate the equation, you follow the same steps you follow when calculating the correlation coefficient R. So you go to Calc, Reg, and then you click on X. And finally, you click on AX plus B, which is the form of regression line we are studying. So there you have. First of all, we can see the value of R, which is the correlation coefficient. You see it's negative 0.997. That's a very strong negative correlation, which is fine because as the more ages the tire has, the more it consumes, or the less kilometers it does per liter. So that's perfectly fine. But then we have these two values, A and B, which represent the coefficients in front of our, or the coefficients of our line, okay? So this is what interests us the most, the value of A and the value of B in this case. So we have those two values. If we go back to the problem, you will see that, let me write that down, y equals ax plus b. From the calculator, we know now that A equals negative 1.34 and B equals 21.9. 0.3 if we round it to three significant figures. So the equation of the line, of the regression line, would be y equals negative 1.34 x plus 21.3. This is the equation of the line. Here I wrote a summary of the steps that you need to follow using your Casio calculator. So if you don't remember how to calculate the regression line, you can follow these steps. Menu, statistics, you plug in the values in list 1, list 2, then you go to calc, reg, x, and ax plus b, and you get the window where you're given the coefficients a, b, and the coefficient of correlation coefficient r. Okay, so that's it for part A. Then part B says, interpret the meaning of the constant value. The constant value is referring to the independent term, which is the value of b. In this scenario, what do you think the value of b represents? The value of b, in this case, would represent the distance per liter covered by the car if the tires were new, right? If the age of the tires were zero or was zero, right? So that's what it represents. It represents that with brand new tires. And what will be the distance covered per liter? It will be 21.3, which is a number greater than 20, right? Because it's brand new tires. So with brand new tires, the car would travel 21.3 kilometers per liter of diesel in this case. Okay, so that's how we interpret the meaning of the constant value in this particular case. Then part C, it says, interpret the meaning of the gradient of the regression line. The gradient, as you may see, is negative 1.34. It's the value of A. So what do you think this number represents? You see, first of all, it's negative. That means that it has a decreasing trend. And what does the value itself represent? It represents that for each year that passes, the car would travel 1.34 kilometers less per liter, right, than the previous year. So that's exactly how we interpret the gradient of the line. So we could say that every year, the car travels 1.34 kilometers less far, we could say less far, but the clue word is less, less far on 1 liter of fuel, or of diesel in this case. So that's how we interpret the value of the gradient of the regression line in this particular case. Finally, for part D, we're going to use this line for prediction purposes. It says, use the equation of the regression line to estimate the distance the car would have traveled on 1 liter of diesel when the tires were 3.5 years old. So 3.5 is a value somewhere in the middle, right? So maybe the answer would be something around 16 point something, right? So let's see. How can we calculate the exact value? Easy. We already have the equation of the line. So once we have the equation of the line, we could just plug in the value of x, which is 3.5 years old, and we would get the value of y. So y equals negative 1.34 times 3.5 plus 21.3. So finally, we get the value of y, which is, let me see, negative 1.34 times 3.5 plus 21.3. This gives us 16.6. 16.6, we're talking about kilometers per liter, right? Over liter. So that means that the car, when the tires are 3.5 years old, we would expect to travel 16.6 kilometers per liter. Okay? In case you didn't understand the explanation of how to use your calculator to calculate the regression line, I've left this same problem solved in a PDF version. So here you have all of the different steps. I think there are 6 steps. Yes, 6 steps for you to follow and find the equation of the regression line. Okay, so this is just for you to keep a record. And that's it for today, people. As always, if you have any questions, you may always ask them through Google Classroom. And I hope you enjoyed this video, and